Guys, if you can please make your phone silent. So we have today's speaker. He's Dr. Vijay Raghavan. He's a director of engineering at MathWorks, and he was our own PhD supervised by Professor Paripati. He graduated here in 1999?
Six.
1996, okay. And that was in fault diagnosis algorithms. And he got the best paper award in Sage.
Yes.
Which is related to that?
It is related to that.
Okay. And he's going to talk to us on model-based engineering at MathWorks.
Thank you very much. Thanks for everybody for attending on a rainy afternoon. I'm sure you have other great things to do, so I really appreciate it. So my name is Vijay Raghavan, and I graduated from UConn with a PhD in '96 under Krishna, so I have a lot of fond memories. 6 years of doing some amazing research at UConn, and from what I gather, it has only improved both the quality of research, the quality of students, and it's great to see a fantastic campus you have. Awesome. I wish I could come back and redo my PhD again, this time for real. Okay, so I want to talk about graphical programming languages and model-based design. That's really what I work at MathWorks. That's what I've been doing for the last 2 decades. Okay. And for that, you can really blame Krishna, because he was the one who taught me this amazing course called Network Flows and Graph Algorithms, which gave me a fantastic grounding in all things related to graphs and algorithms. And that really paved the way for me to get into programming languages and compiler technologies. Okay. So thank you, Krishna.
I don't know anything about what you do. So.
Well, you have created a monster. Okay. So this is, it's a funny quote. I was there when he said it. This was at MathWorks automotive conference a couple of years ago. This is John Lance from Volvo Car Group. He said, when I step into a new car these days, I don't smell leather anymore, I smell software. Right? And it's absolutely true. And it's shared by, it's not just his opinion. This is the CTO of General Motors. He was talking about the amount of code that's part of today's car. Like if you go from 2000 to today, it went from 1 million all the way to 100 million. Okay. So it's just incredible amount of software, right? And going forward, there are 2 other driving factors that are driving this megatrend. One of them is autonomous systems. Okay. Everybody has heard of it. Then there is industry standards. The fact that there are the California emission standards are getting stricter and stricter, or fuel economy standards. These are all the standards that actually force companies to innovate much faster than they normally would. And as a result, well, the only way you can do that is through software. I think it was Mark Andreessen who said, software is eating the world. And it is absolutely true, because it's in everything and it's everywhere, and it's growing exponentially. Okay? So, question is, how do we manage this exponential growth of complexity in our systems and our software? Anybody know who this is? Usain Bolt. Okay, he was the fastest man on the planet until a few months ago when he retired. So, if you want to scale up, you could run fast. You could work really hard. Yeah? You could do that. You could be Usain Bolt. You could be the Usain Bolt of programming. Now, you may think he's really fast, but he doesn't stand a chance against this puppet right there. So, sometimes scaling up means not just raising your game, but playing a different game. And I'll tell you where I'm going with this. Isad, good to see you.
You too.
Abstraction. Yes, he did an internship with MathWorks a couple of summers ago.
Okay, yeah. He took my machine learning course.
I hope he did that.
I passed.
Good. That's fantastic. Okay, so abstraction. That's how we're going to tame this beast. What is abstraction? You transform a hard problem into an easier problem. And one of the answers that I would like to talk about is high-level languages. Of course, there are different ways of thinking about abstraction, different ways of providing abstractions in our workflow. But at MathWorks, we look at high-level languages as a way to provide you the abstraction you need to tame the complexity in your systems.
I think that's the best definition of abstraction I've seen.
Oh, thank you.
Yeah. Because I see a lot of people talking abstract, all these computer science guys, and never understood. Okay.
Any computer science guys here?
Always insult them.
Okay. So, question for you. I'm assuming almost everybody here has at least heard of MATLAB? Yes? Okay, good. How about Simulink?
Yep.
Any Stateflow users? One. Okay. Okay, great.
Battery stuff.
So these are the three high-level languages at MathWorks. MATLAB, Simulink, and Stateflow. Okay. So MATLAB, everybody knows about it. It is a high-level textual programming language which gives you matrix operations as primitives. Okay. So you don't have to write for loops. You just do A plus B. It does the matrix addition for you, and so on and so forth. So, and it's not just the matrix operations, but it gives you a rich set of libraries, a fantastic technical computing environment, and visualization. So together, it gives you a nice package where you could do a lot of really interesting stuff really quickly without learning software engineering, really. If you don't want to, you don't have to. Okay? So that's the beauty of MATLAB. Now, Simulink is our second platform at MathWorks, which is it's a graphical programming language. If you haven't used Simulink before, it's a very simple description of Simulink. Imagine a graphical canvas where you put blocks. Okay? So there are blocks that represent, each block represents an algorithm, and it has inputs and outputs. And a block of an algorithm reads its inputs, makes a computation, produces output. And you connect these blocks up. And the data flows from left to right, or along the arrows. So roughly a data flow type of computing environment. And the third high-level language we have at MathWorks is Stateflow, which is used for designing state machines. Not just finite state machines, but hierarchical state machines with hierarchy and parallelism and a bunch of things. Now, anybody here has not heard of a state machine before? Anyone? Finite state machine? Everybody knows what it is? Okay. Just in case, if somebody is listening in who doesn't know what it is, a state machine is really simple. It is a model of computation that exists in nature. Okay. A light switch is one of the simplest state machines you can think of. It has two states, on and off, and you move between these two states based on external events. In a case of a light switch, it's you flicking the switch, right? So it's an event-driven system that moves between states. So I worked on Stateflow from day one. For the last 21 years, I've been working on it. And as a result, I'm biased. I really love this programming environment. Now, I'll tell you one other deep reason why I appreciate state machines. So at MathWorks, we do a lot of programming, a lot of software engineering. And we have a whole bunch of teams. Different teams work on different types of programs. And we all have bugs to fix. And over this long period of time, when we look at the bug statistics, we find that some teams don't have a lot of bugs, and there are some teams that have a whole bunch of bugs, right? So when we analyzed what was going on, this is what we found. So at MathWorks, we make toolboxes. Okay, toolboxes are these nice little functions. You can call those functions, you get an answer back, right? So toolboxes typically have fewer bugs. It's actually easier to debug them, easier to get them right. Okay? And then we have tools like Simulink and a whole bunch of other tools where there are a lot more bugs. Somehow the bugs don't seem to dry up. And the difference is this. A toolbox function is a stateless entity. It is a function which has inputs and outputs. There is nothing inside it. You call it, it gives you an answer, right? Whereas a program which has internal state in it is much harder to debug, much harder to ensure quality of. In fact, this is something that I'm sure if you look back at some of your own programs, you will probably notice the same thing. The programs with state have more bugs. They're harder to design and harder to debug. Okay? So that's just an empirical story. So state machines are finite state machines. Everybody knows what they are, I'm assuming, right? States and transitions. State charts or hierarchical state machines, they just give you, they take FSMs and they give you hierarchy. That means you can have states inside states. So in here, I have passive, active, standby, off, and it all belongs to a superstate called L1. And it also gives you parallelism. You can have simultaneously active states. So parallelism and hierarchy, they give you a way of constructing really large state machines without constructing thousands of states. Okay? So I do want to motivate why state machines. Okay. So let's take a simple problem which on the surface doesn't look like it's a state machine problem. So it's a data analysis problem. Say I have a stream of data and I want to identify large or contiguous regions in my data that satisfy a certain property. It's a fairly common problem that we see most people doing. Now, the only thing is my contiguous region needs to satisfy a certain property. Suppose, let's say, the property happens to be a threshold. It's very simple. So in my data, my abnormal region starts when the sequence falls below. Oh, wait a minute. Sorry. This is interesting. Looks like I missed a slide. Okay. Okay, sorry. So it looks like the problem, I had a small problem with my description. Okay, ignore the previous slide. You have not seen it. Okay, so I want to identify a region that falls below a certain threshold. If so, I can write a simple for loop through the data. If my in data is greater than a threshold, I pass input to output, otherwise set it to 0. And if you are a MATLAB hacker or a good MATLAB programmer, you can do it in one line like this, okay? Or you could do it as a state machine. I have two states, normal, abnormal, and I go between these two states based on these two conditions, u less than t, u greater than or equal to t, and I do the equivalent stuff in these two states. So at this point, it looks like the state machine is an overkill. And this slide was not supposed to be there earlier. Okay. Now, you see the slide that you're supposed to see. So I make the problem slightly complicated where it's not a single threshold anymore, but I have different thresholds. My abnormal region starts with one threshold, and the normal region starts with a different threshold. At this point, my code becomes a bit more complicated. By the way, don't worry about trying to read this code all the way from the back. In fact, we don't want you to read the code. It's complicated. But basically, in order to do this, I need to keep track of which region I'm in, blah, blah, blah. Whereas the state machine looks pretty much identical, where everything is the same. The conditions have just changed from T to T1 and T2. Okay? Then let's add one more wrinkle. Not only hysteresis, but let's add debouncing. So debouncing is a process of being resilient to transients. So I have a whole bunch of data samples. Just because one data sample falls below the threshold doesn't mean it starts an abnormal region. I want to wait until a few of those samples fall below the threshold. So now I say, well, I have this buffer of N1 and N2 samples for which I need to observe. Only then I need to start and stop my regions. So once I do this, the code becomes so complicated, I actually had to change the font so I could fit it on one screen. Okay? Once again, don't try to read it. But here now I have to maintain counter variables and all sorts of stuff. And state machine looks identical. Now, you could say I cheated here a little bit because look at this. Here, I'm using an operator called count. So this is a high-level semantic operator in stateflow. What it does is, what it tells you is this. When I'm in state normal, if this expression holds for this amount of time, that's when I take this transition. So you can do it. So basically, it looks the same, right? Moral of the story, as the problem gets more complex, your code becomes more and more complex. Okay? Whereas your chart remains concise. Look at this, approximately the same. Now, notice that there are other types of complexity that arise, that can arise in your problems, such as substates. There could be different types of normality and abnormality. And that can also give you a whole bunch of extra variables. Yeah? Whereas within stateflow, you just drop in a couple of substates and you're done. So notice that stateflow is a high-level language not just because of its graphical nature, but we have a whole host of high-level semantic constructs that capture common design patterns that you try to implement in your own code, and we abstract them out as operators that you can use. We have a bunch of other ones on temporal operators and change detection and so on and so forth. Okay? So state machines, they're everywhere. So I gave you an example of a light switch, but that's too simple. It is a calculator. You would think a calculator is a simple numerical computing machine. Why is that a state machine? Turns out that this simple, by the way, this doesn't have any mathematical operators. It's just doing simple operators, okay? This calculator, believe it or not, it has a state machine, okay? Maybe hard to see, so I'll describe. So at the heart of it, there are two major states, a number state and an operator state. That means you're either typing a number or you're clicking on an operator. And depending on what you do different things. But let's take a look at the number. By the way, this is where the hierarchy of state flow becomes really, really handy. This is not just a leaf state. Inside there is detail, okay? So why is number so complicated? Anybody guess? Any?
Decimal notation.
Yeah? Decimal notation. Okay, you're on the right track. So you must be in computer science. Okay, so imagine what happens in a calculator. When you turn on the calculator, what do you see? You see 0, right? And if you keep pressing 0 lots and lots of times, what happens?
Nothing.
Nothing happens, right? It stays at 0. But the moment you press a number which is non-zero, that's when it starts accumulating digits. It's either a non-zero or a decimal, yeah? So those are your states, right? You stay in the 0 state, and unless if the button is non-zero or decimal, you start doing different things. Otherwise, you have to stay in the same state. So something as simple as number entry is an interesting, it has surprising complexity to it. And imagine writing code for a calculator if you're trying to do it. Okay? This is what you would deal with, right? So state machines, once again, they're everywhere. I'll give you one other example to motivate state machines. In communication systems, there are a whole bunch of protocols. Okay, this is a very simple protocol. It's a real one. Apparently, this is used for transmitting the current time. So your phones and other things can synchronize with respect to the time signal. So at the heart of it, it's all pulses, ones and zeros. Every 10 seconds, there is a 770 millisecond pulse is sent. So you get 77 ones. And at the beginning of a frame, you get a 0. And if it is 0 followed by 17 pulses, 17 ones, then it's symbol A. 0 followed by 47 ones, it's symbol B. Okay? Now, the challenge here is if you're building a software receiver for this protocol, when you turn it on, you have no idea where you started off in the sequence. Okay? It's because the signal is there. So you need to be robust to your observation, which could start in the middle of a symbol. If so, well, you can't do anything, you can't retrieve it. You could just throw it away and start with a new one. So there is the synchronization phase. So it turns out that it can be implemented as a very elegant state machine. So the first thing that you do is you search for a marker, that's a state, and you stay here until you receive 77 ones. Okay? If so, it could be a new frame. It doesn't mean it is a new frame. Because if it is, the new frame has to start with a 0. So only when you receive a 0, that's a new frame. Then from there, once again, if you receive 17 ones, it could be the first symbol, but not quite. It has to be 17 ones followed by a 0. Only then it's symbol A. Otherwise, then you keep looking for symbol B, which could be 47. So when you're at 17 ones, you don't know whether you are in symbol A or symbol B. So that's why you need a state machine. And then if you receive more than 47 ones, once again, you have no idea. It's not B. Probably it's a marker, right? And that's a state machine. Okay. And just wanted to put it out there. This was one of the proudest moments of my career. The year after we shipped Stateflow, NASA used Stateflow to automatically generate code that went into space on Deep Space One spacecraft. It's quite far away now. After about 3 or 4 years after it was launched, it left the solar system. So I'm positive it's it's in outer space somewhere. So this code, it's guaranteed it's going to outlast me for sure. So I'm immortal. That's great. So with great power comes great responsibility. And I always thought it was Spider-Man's uncle who said it, but apparently not. It was attributed to Voltaire, who was an 18th century philosopher. Google told me. So what I mean by this is, well, I talked about this beautiful, amazing, powerful graphical programming language, but is that all? I mean, that's not enough, because if we are providing you this powerful graphical programming language, which is extremely expressive, and if it allows you to concisely describe complicated things, it should also allow you to debug, to detect errors. And pretty pictures are no good unless you can deploy them into a target of your choice. Could be a CPU, embedded system, or FPGA, and whatnot. So we need all of these: simulation, debugging, error detection, and code generation. So what I'm going to do is I'll jump into a quick demo, for which I need to be close to the computer. So I apologize, the left window here looks a little bit washed out, so it's kind of hard to see what it is on the projector. So I will describe what I'm doing here as I'm clicking away. So what I have here, let me jump into the state machine. What I have here is an abstract model of control module for a drive. Okay? This is a real example that we got from one of our industrial automation customers. So these are a drive moves things from one place to another. They're typically used in packaging machines. Okay? And the drives are, they're pretty mindless. They just move, right? Move, stop, start, and so on and so forth. And there are commands that somebody gives them. Start, stop, move, reset, hold, and whatnot. But when the command comes in, if the command is directly piped to the drive, bad things can happen. Because if it's already moving, you don't want to move it, and so on and so forth, right? So you need to have an intermediary, a state machine that takes the commands and observes the state of the drive and does the right thing. Okay? So that's what the state machine is about. So I'll talk through it a little bit. So this state machine has a bunch of states. The drive starts out in idle, and when it receives a command called start, it goes to started state, and it calls a function called start drive. And at this point, if it gets a run, it goes to another state, and then there is a reset command, and so on and so forth. There is also some kind of, so you could hold it, you could restart it, you could stop it. So it's capturing a fairly complex protocol that the machine has to adhere to, okay? In addition to fault detection. So these drives, they do run into faults once in a while. And when they do, sometimes it's a simple fault. So you just reset it and it fixes itself. Sometimes it's a fairly complicated, unrecoverable fault. In that case, it doesn't fix itself, right? So that's a state machine. And you could, in Simulink, you can actually build some dials and gauges to control the state machine and see what happens. So what I'm going to do is I'll just, let me run this guy. Okay. So hopefully you should be able to see some animation. So what I did was I clicked on start. When I send in the start command, it went from idle to started, yeah? And by sending different commands, I can make it do different things. Let's say if I click on hold, I should go from started to holding to held, yeah? And I say, well, what happens if I press restart? Well, it should come back and it should do the right thing. And I can also inject faults using Simulink, okay? That's one of the things you could do with a simulation environment. In a real machine, you don't want to inject faults because machines are very expensive. So you do it in simulation. And you want to know what happens. So if I have, if I have a simple fault, the logic says I should stop and a reset should fix it. So I'm going to reset it. So now that it's reset, it goes back and the simple fault disappears. Okay? And if it's an unrecoverable fault, let's see what happens. Then it doesn't recover, so it just keeps doing this. That's my design. So at least now I know that it's doing what it's supposed to. Okay. So as you can see, it is a fairly complicated state machine. So I tested a few things, but I have no idea. It's got so many transitions, so many conditions, so many states that I have no confidence that I will be able to manually inject the right set of events and commands to hit every single transition and reach every single state. So I don't know if I can do that. So fortunately, we have the ability to analyze this diagram statically and try to generate automatic test vectors. Okay? So let's do this. So I'm going to right-click on my chart, find the design verifier, and I say generate tests for the subsystem. Okay? So we have this amazing product called Simulink Design Verifier, which uses our internal compiler infrastructure to convert a Simulink stateflow and even MATLAB code into an intermediate representation that can be analyzed to do static analysis, property proving, as well as automatic test vector generation. Okay? So what it's trying to do is it's trying to create input sequence vectors. such that it can hit every transition. Now, the full coverage means you want to hit the transition, you need the transition to be both true and false. Yeah? If the transition is always true or always false, that means you miss something. So think of an if statement. You need to hit both sides of the if statement. Yeah? So let's see what happened. So it created a bunch of tests and all that, but there is a problem. Okay? Look at this. It says analysis of transition. Transition trigger expression was unsatisfiable. So it found a transition it could not cover. For whatever reason, no matter what it does, it says, I cannot take this transition. So let's see what the transition is. That happens to be transition 67. Okay, right here. So now the static analysis is telling me that it cannot take this transition. Okay, and I wonder why. I have no idea. Let me look. So here, I have two transitions leaving this state. Transition 1, okay, and transition 2. The first transition leaves, it's taken if command is stop and if there is a fault. Or if there is a fault. Yeah? So now, this one says, oh, command is stop, take it. So, if command is stop, I will always take this transition and never this guy. So, this transition is shadowed by the first one.
It's a subset, right?
Yeah. But the thing is, it's a typo. See, this is stopping, this is aborting. I was supposed to type C abort here, not C stop. So, true story. This is a model, this is the demo model that I put together many years ago from a spec that was given to me by one of our customers. And I made that exact error. I did make that error. And when I did the design verifier check, it found the error. I liked it so much, we shipped this demo exactly as is, just so that I can show you what it did, right? And when this tool works, it's magical. And the trick is to get it to work. So, in this case, it's a human error. C abort. So, since even though I'm biased, I'm from MathWorks, I objectively think that a model like this is very hard to debug on my own without static analysis tools. Especially a small typo in a large state machine is very hard to find. Okay? So that's why you need really powerful tools. So now that I found the typo, I go back and I try to do the design verifier generate tests again. So now it should go through and it should give me 100% coverage. So far so good. Okay, I don't see any red. Okay. Trust me on this, it's going to finish soonish. Okay, 57 out of 57, it's done. So now let me show you the test vectors themselves. So first of all, it analyzed the diagram. It found that it can cover all parts of it, and it automatically generated test vectors that take me through these different states. And these are the test sequences, by the way. Okay. So this is called a signal builder block, which gives me all the test sequences. Look at the number of test cases it generated, 28 of them. And the initial set of test cases are simple. The command stays at 1, doesn't change. But let's take a look at test case 19 or 27 maybe. Look at this. So here, this is taking the command through various contractions, and there is no fault here, but then it's doing a bunch of things with the drive. These are all the kind of things that, yes, one could be very creative and come up with all these scenarios, but the tool does it for you. So that's the beauty of analysis. And this is exactly what you need when you're dealing with high-level languages. Okay? And finally, I want to show you code generation. So So now that I've verified that it all works, I'm all happy with it, I can right-click on this block and say, build this subsystem. And the same compiler infrastructure can be used not just for analysis, but for simulation as well as optimized code generation as well. Okay? And the code that we generate from these languages, it has to be highly readable. In fact, our customers insist on it. And not only is it readable, it's fully traceable. So for example, here is the code that it generated. So I have bidirectional traceability from the code to the diagram to code and whatnot. So let's see, I can right-click on the transition. I can say navigate to C, C++ code, and it tells me, it shows me the exact lines of code that represent the transition. It says, look, the command is C start, do this stuff, mark it started, and so on, and then call start drive. Yeah? So it's fully traceable. You can go back and forth between code and model. Okay? So now let's go back to the presentation. I do want to leave some time for questions, so we have some more time. Although, if anybody has any questions that cannot wait, I can take them. Any questions?
When you're generating your code,
Yeah.
So you're creating some models. Are they templated or are they're specific, specific types? Can you use them in a very abstract way and operator overloading, or are they?
So you're asking about the code that we generate, the actual the code that we generate. Are they specific to the model, or the templarized so you could take them and kind of change the sizes, parameters, and so on?
Yeah,
that's an excellent question, by the way. So I just want to repeat the question for everybody. So this is something that we do hear from a lot of our customers. So what our customers do is they develop models and code where they have to hard code the sizes of certain vectors, but the algorithm itself is written in such a way that it is pretty generic and size independent. And when they generate code, they'd like to see the code come out where the sizes of the vectors are not hard coded. It's not for I equals 1 to 10, but for I equals 1 to n, and n can be pound defined somewhere where they can change it at compile time. So historically, we have embedded the sizes in the generated code, just hard coded the sizes. The reason for that was when we compile this high-level language, when you define a size somewhere, unfortunately, it has a way of percolating through your entire code, and it opens up certain optimization opportunities which we don't want to pass up. So as a result, we have to take advantage of the actual sizes of the vector, and they do get hard-coded. Plus, sometimes it just makes things a lot easier to know the size of a variable when you're generating code for it. But we are working on a feature that will allow you to mark a certain, a few vectors as, look, these vectors are templatized, don't depend on the sizes in the rest of the compilation. Once you do that, those vectors, they become fully parameterized. And we don't take advantage of the size information to do optimizations. So you lose a little bit of optimization, but you get templatized code. So this is not out yet, but it will be soon. Okay. So coming to the end of the presentation, it actually went faster than I imagined. I don't know why. Okay. 97 was when we released Stateflow 1.0. Okay. 97 was also the year when Deep Blue defeated the then chess champion, Garry Kasparov. I don't know if anybody was alive during that time to remember this, because I see a lot of young faces. So this was a huge deal. I thought I would never see this in my entire life. Right? then just suddenly one day, the computer defeats the human being. So I was quite depressed for a while. I thought, that's it. Human beings, you're done for. But it turns out that at least in that case, the truth is a little bit more complicated. Yes, the computer defeated the human being, but the man behind the machine was Joel Benjamin. He was a chess grandmaster. Now, admittedly, he was not as good as Kasparov, but the combination of the human ingenuity and the raw computational power of a machine was just unbeatable. Okay? And that's a good lesson for all of us, because there is quite a bit of fear among people, everybody, that automation is coming and it's going to make a lot of us necessary. But I don't believe that. At least those of us in this room, I'm sure, have enough skills that can add, not subtract. So automation needs your help, needs our help, because computers are stupid. It's really humans who make them smart. And world-class automation tools like MATLAB, Simulink, Stateflow, and somebody said Julia this morning, I won't name who it is, they do need world-class researchers, because these are trying to solve problems that are very different from the traditional tools we've been using. Right? So as system engineers, your expertise is really important. Okay? Not just in building the tools, but sometimes in just using it and defining the problems and finding the boundaries of where the tools fail, so that you can tell the tool makers to improve it. Okay? So whether you are a tool maker or a tool user, you can contribute to the automation. The wave of automation, it is the future. And guess what? If we don't do it, someone else will. And I don't want that. I don't want them to get all the credit. In fact, I want you and me to get all the credit if possible. So this is a small sampling of interesting problem areas in model-based design. It's a whole bunch. It's not going to fit on this screen. But the ones that I've been thinking about, I feel passionately about, are language design. I just put a couple of random things here, such as efficient ways of denote graphical variance. Now, variance is a concept that keeps coming up again and again. Where if you look at a automotive manufacturer, they don't have hundreds of different designs. They have typically one design and 100 different variants of the same design. Okay? And they do that with not just with the mechanical systems, body and all that, but even the software. They have, whether you buy a Toyota Corolla or the high-end Toyota, whatever that is called, it has essentially the same code compiled into it, but maybe sometimes a different compile flag, so that one of them has one algorithm, the other has a different algorithm. But really, they just have one piece of code. So variance is a big problem. And how do you manage graphical variance and compile them, analyze them, generate efficient code from them? It's an interesting problem. Sure, there are different ways of solving it, sure. But as an engineer who works at MathWorks, as a tool maker, I'm interested in the ones that are not necessarily optimal, but they are near optimal or good enough that can be implemented today, if possible, right? And combining state charts and physical domain. This is another area where I think it's pretty exciting, because there's a lot of interesting physical systems that are state-driven, and there are ways in which you could do it, but doing it very elegantly in our tools is something that we are looking into. And of course, code generation this is an area which has really taken off in the last 10 to 20 years. MathWorks now generates code from all of our languages it lowers them to C, C++, VHDL and Verilog, so that you can actually take these designs and synthesize them into FPGAs and ASICs. And our latest code generator is for GPUs. It's pretty hard. If you're doing any kind of image processing or deep learning or any kind of computationally intensive MATLAB program, you might want to go to GPUs because the speed up that they're going to give you is just fantastic. And of course, targeting heterogeneous hardware, that's actually pretty relevant as well. Because these days, you don't just buy a board with a CPU. Most people, they want to buy a board with a CPU and some kind of accelerator. The accelerator could be a GPU or an FPGA or a custom vector processor. Okay? So taking a design and partitioning it so that one part goes to the CPU, the other part goes to the accelerator, that's an interesting problem. Partitioning, efficient generation while reducing the overhead, and verification and validation. Now this, I'll tell you, I can see in about the next 10 years, graphical language is good enough. You may not need much more. Automatic code generation, it's done and dusted. But this verification and validation, I think there is at least another 100 years worth of work here, or more. Because the more complicated our systems get, the more complicated the verification problem is. Now, the design verification tool that I've shown you is really, I think of that as a start, because it's hard for these kind of tools to scale up to models that have tens of millions of states. Right? So those are all the things we need to work on. Quality of service estimates. And this is also really critical when you're designing a really large system. You want to know whether the load balancing is appropriate or not, whether the system is responding properly. And today what's happening is, because you cannot estimate them properly, you can do it during simulation, you can do it during analysis, you have to wait until the full system is assembled, and it's a very expensive proposition. And finally, safety and security. I'll tell you, my big nightmare about driving an automated, a car with a lot of software is this. Okay, I don't want Russian hackers to come in and crash me into a tree. Of course, I'm not that important, so Russians won't get to me, but somebody else might. So safety and security is really important. I mean, by the way, it's true. But think about, I mean, it's a bit sad, but we had a terrible incident in New York with the guy driving a truck in the bike lane. Okay? And we caught the bad guy, fine, but what if there is no bad guy? What if the bad guy programs the truck and sends it on its way, right? You don't want that. I mean, it's going to be a world of nightmare that I don't want to live in. So safety and security of the systems that we put on the cars that we drive, the planes that we fly, are really, really important. So this is just a mere taste of the interesting problems. I'm sure there are many others that you yourself are working on. So last couple of slides, I just wanted to leave them with you. I'm representing MathWorks product development. I work on making the tools. But we have an entire department that works with academia, that works with researchers and students and professors to help you with using our tools both in your coursework as well as research. So it's called the Customer Success Team. I thought it was called Academic Support Team. Okay, CST. So one of the gentlemen, Balaji Sharma, he was here a couple of days ago. Some of you may have met him. So he asked me to put this slide again. That's his email. And he can help you with curriculum development and research computing and so on and so forth. And I think it's the same slide again. And then, yes, finally, I had to end with a picture of pugs because I love pugs. I have a pug. Okay. So that's the end of the talk. And questions? We have at least 10 minutes. I take it? Okay.
Thank you very much for the talk. So it seems like there are conditions that govern the transition between the finite number of states you have.
Yeah.
My question is, would it be possible to have, let's say, a threshold based on probabilities and have stochastic transitions between states?
Brilliant question. So just to repeat the question, you want to know whether it is possible to build a state machine where the transitions are guided by probabilities. So it's not about the condition being true or false, but you take different transitions based on probability. You can do it today. It's very easy because the language that you can type on the transitions and states is MATLAB. So any MATLAB code that you can imagine, you can use on the transition. So call your favorite random number generator, okay, or roll your own, and you can call those, and yeah, you could do it. Absolutely, good question.
Thank you.
Seems like so can you outline some of the technologies that are behind the simulating design verify? Do you use any model checking tools, or it seems like there is no formal specification per se,
Okay.
but you're still doing something which seems to be in the area of model checking. So can you elaborate more on that?
Okay, good question. So you wanted to know what's behind simulating design verify? How does it work? Because it's a short talk, I didn't want to go into the details of it, but I can give you a quick high-level summary. We at the heart of it, we have a theorem prover. It's made by a company called Prover. It's a European company. The only thing that they did was they made this SAT solver-based theorem prover, which is used by railway companies to prove the correctness of the signaling systems. Okay? And it's just a raw engine. That's all it does. It doesn't know anything about the environment. So we took that engine, and what we did was we took our models and we lowered our models to that low-level binary representation that they can handle. So yes, at the heart of it is a theorem proof. Does that answer your question?
Yeah.
Okay. And they do have a language called Tekla, but it's a serialization language, so I don't know if you've heard of it. I don't think we document it, but if somebody wants to know, they can always look at it. Any other?
In the interface of the test case generator, what kind of questions I can ask other than reachability? Can I ask, is there a loop in the state machine of length 3, let's say?
Oh, great question. So the question is, what else can you do? Can you just generate test vectors, or can you do other things? So once again, I did not have the time to go through the whole thing. There is, we have a language that you can use to specify properties, okay, and constraints. So you can define constraints on the inputs to basically narrow down your search space so that you're not looking at R infinity, and you can then that's on the constraint side. Then you can define properties to verify. That is, you can take an expression and say this expression should always be true, or sometimes true, or it should be true after some other time. There is we are also introducing what is called metric temporal logic, MTL. Have you heard of it? Yeah. So there is going to be some MTL support as well. So you could do a lot of interesting and sophisticated things. So the language allows you to do a lot of interesting things. On top of that, we ship a bunch of pre-built primitives that just make it easy to put a bunch of things together and use them. Yeah. So let's say if you want to do the whole loop stuff, right? You could actually code it up using these different proof properties, where you can say, I have to go from here to here first, and then you can define a sequence that has to be true during simulation.
Could you tell us some stories how state flow evolved in terms of requests from your clients?
Well, there are a lot of stories, but we don't have time for stories. However, I can make a general statement about the evolution of not just Stateflow, but all of our MathWorks products. We believe in a closed-loop system. Okay? We do not develop features, open loop, where we just imagine, hey, this looks like a fun thing. We do it because somebody wants it. Because there is a problem that cannot be solved using our existing features, then we do stuff. And the way we get that feedback loop is through various mechanisms. sometimes it's as simple as a user contacting us through customer support, just sending an email. But we also have a lot of outreach events during the year where we meet our customers. We have many conferences that happen around the world where development representatives like myself just go meet people, talk to them, get some feedback. For example, your templatized request, it was something that we heard from other customers. Now that I heard from you, I'm going to make a note of it in my trip report. Okay, and pretty soon you're going to see a release note saying, hey, this is fixed, and you'll be happy, right? So that's what we do. I mean, unless we talk to you, we don't know what next to do. So it's really important for us to stay really close to our customers, be engaged. Any other questions?
Yeah, maybe we can talk a little bit about how you did the test design thing, like 28 or whatever, that you came up for your state machine thing.
Oh, that's automatically generated.
Right.
That's what I was saying.
Yeah.
So
what is the...
Okay. So what happens is basically, in order to do that, we put in instrumentation in the states and transitions saying this state should be, basically, the properties that you want to prove, right? Mm-hmm. So the state activity is a variable. So we say that, well, this variable has to be 1. And then for every transition we create a variable, it should be both true and false. So once again, there is a prove true and prove false. So the intermediate representation gets instrumented with lots and lots of auto-generated proof statements, right? And then we throw that program to the prover and say, try to prove these by doing whatever you want with the inputs. Mm-hmm. So it just searches the input space and tries to figure out.
So it's like the ATPG thing that we just do.
Yes. Okay. Yeah, exactly. But we try to optimize. The thing is, that's the concept, right? But in reality, you have to do a lot of tricks, computational tricks, to make them scale. Otherwise, right, you'll solve really small problems in a long time. Right? That's where most of our work is, like make them scale.
What's the largest system that you could think of being automatically tested using the current simulating design verifiers? As in, do you think it will scale for, say, composition of thousands of states or hundreds of states? Where is the order?
Okay, so the question is about the scalability of this technology. As I mentioned, scalability is the number one problem with a lot of these techniques. So fortunately, Prover is the proof engine that we use is actually very efficient with integers and booleans, integers, and enumerations. Okay? And also, so state machines, not a problem. You can throw really large state machine, no problem, it works. Where it becomes tricky is if you have nonlinearities and floating point numbers in your diagram. So nonlinearities make it really hard. That nonlinears typically kill the analysis performance. So for that, one of the approaches we are taking is nonlinearities in the presence of floating point quantities can be transformed to nonlinearities with integers by lowering the floating point operations into integer operations. So essentially, assume there are no floating point numbers, you only have integers, and when you add two floating point numbers, we will do all the floating point math behind it, right? As if there is no floating point coprocessor. That seems to help. Good question.
Okay, let's thank Vijay once again.